positively charged solid metal sphere is isolated in space. The electric field strength is measured for different distances from the center of the sphere. The variation with x of the field is shown. So you imagine you have a really big sphere right here, and you just measure the electric field strength from the sphere, because you don't know it's positive or negative, or never mind lah, we just draw. So this is how electric field would look like, and we just gonna measure that. Okay, what do we need to find? First part says, suggest y for values of x less than 4, which is right here, the electric field strength is 0. So if you look at this shape, this is probably a sphere, not a point charge. So you're going to have electric field go stronger and stronger and stronger, and suddenly it drops down to 0. What's happened here? Why is it 0? Now you might be tempted to say, oh miss, because it's inside the sphere, that's why it's 0. But that's not the reason. We want the physics reason why it is 0. So here's what we can say. It's kind of a standard theory. Imagine you have a charged metal sphere. Let's choose a nice aluminum sphere right here. Oh, that's very bumpy. Okay, sure. And I put some charges inside there. And these charges, they will spread out as far apart from each other as they can, all along the surface of the sphere. Okay, because they don't like to be close to each other. Eventually, they'll find their equilibrium position and stop moving. So at this position, actually, if they are not moving, it means there is no net force on them. No acceleration. No net force on every single charge means, well, FQE. If there's no force, there is no electric field strength, or there is no resultant electric field strength. So the resultant electric field strength is 0 everywhere inside the sphere. If you're not convinced, you could try to pick a point and you try to draw the electric field of every single charge particle on it. And you will see that, well, if you draw a lot of charges, they all kind of like point in all different directions, but they cancel out inside this circle of charges. So that is the reasoning we need to say. So we can say the charges in the conductor are not moving. In the conducting shell or conductor are not moving or accelerating. Accelerating, not moving. And are in equilibrium. This is the idea of no net force on each charge. Because there are so many of them, they all cancel out, pointing all direction. So then we link it to electric field. So due to the relationship between force and electric field strength, therefore, electric field is also 0 inside the sphere. Electric field is 0 inside the sphere, which is less than 4 cm. It is an extended answer, but what they're looking for is mainly no net force, no electric field. So this part, equilibrium or no net force. Okay. This is 1. And you want to talk about why is there no net force? How do you know? Because the spheres, once they spread out as far as they can, they stop moving already. They're in equilibrium position. So not moving, not accelerating. This is the other one. Okay. Last part. Now this one is a killer question because there are so many methods to do this. Some might need some thought. If you've never done this before, it's quite a rare question. So let's see. A point charge moves from a point where x equals 7 to a point where x equals 5. This point charge is another charge that I bring into the picture. Use the graph. So we need to use the figure to estimate. This is the second keyword. Means you might not get an exact value. You need to estimate the change in EPE of this point charge. So it's kind of like saying, well, you have a big charge here. And you have a small charge that will go from 7 until 5. 7 is somewhere, oh, where's 5, 6, 7? 7 is here. Draw a nice dotted line. Okay, the charge is here. And it moves closer until 5. Dot, 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 dot. goes here. Okay, because of that shift, that movement closer to the main charge, you will have a change in electric potential energy. The question is how to find it. Your first instinct may be to think of, wait, miss, we know equation. EPE, electric potential energy, is KQQ over R. Can you see this one, right? Yeah, but we have a problem with this method. We don't know what is big Q. There's two charges, remember? One big one here and a small one that is flying around. The big one is Q. The small one is small q. That one they give to us. What's the value of small q again? 8.5 times 10 negative 9. We know this one. 8.5 times 10 negative 9. The big one we don't know. So we have a problem here. We cannot find q. There's a way to get around this method, but it's not recommended in the mark scheme, so we'll save it for later. So we can't use this. Not enough information. Second method, or the main method which I recommend, is to know the four pillars and find the area under the graph. What does that mean? Okay, never mind. Let's recall a bit the four pillars of electric field on this side. So first we have force, F. We have field strength, E. We have potential, V. And lastly, we have potential energy, which is what we want to find. Potential energy. What symbol shall we use? Let's use electric potential energy. Okay. So you want to move between these fields. You start off here. They give us an electric field graph, but we want to eventually get to potential energy. We want to find what is this. So you need to think of how all these pillars relate to each other. How can we eventually go from E field to potential and then potential energy? Let's think about the links. So this first method goes like this. E field and potential are related by differentiation and integration. Electric field is known as the potential gradient. So this is dV dx. But we want to get potential. We want a V equals to something something. So we need to think of, okay, what is the opposite of integration? Differentiation. Okay, so we need to opposite of differentiation, integration, right? Okay, yeah. So you want to find V. That means you have to do E dx. So that's how we find V if we have E. Okay, next step. So we found a way to link E and V. How about V and electric potential energy? This one, we have seen the equation before in the form of W equals to Q delta V. Work done equals to QV. Remember this one from AS? You may see it otherwise as maybe not W, but EP equals to QV or U equals to QV. They're all the same electric potential energy. So from this equation, we want to find what we want to find? Energy. So Q times delta V. Okay, or U QV. What am I writing? QU, QV. Okay, so let's write out the final here. We want to, in the end of the day, find U equals to QV. And V is the integral of E dx. When, in easier words, it means, not this big Q, this small Q, a small charge is flying around. So Q times, when you integrate E with respect to X, you're finding the area under the graph. So this is Q times area under the EX graph. This is how you can find your potential energy or EP or U. I cannot make up my mind. Area under the graph. So if you look at this side here, I'm going to shade out the area under the graph for you to see. We got this nice blue area. If you're wondering, Miss, how to find the area? You have to count the boxes. Like legit count how many boxes are in this blue color area. You know what I mean by counting boxes? Okay, let's go in. Make it big as we can. This is the traditional way. You could also do some geometry here and say, okay, let's cut this off here. How many boxes are in this bottom part? Well, Let's do some maths, I guess. This part has 1, 2, 3, 4. A 4 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 4 by 14 boxes. Okay, then the other one is kind of like a triangle. You could estimate. That's why they say estimate. So for this side, we want to find the area. We gotta do half times base times height. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 can already lah. So that's rough estimation method. Counting boxes. Or you can say, Miss, I just want to find the area straight away. I don't want to count boxes. Okay, sure. Then we can just do some alteration. What is this value? 5, 6, 7. This is 7, right? So this is 2 centimeters. So right here, or. So you have 2 cm times the height, which goes from 0 to. What is this value? 22, 24, 26, 28. So that is 28 Newton Coulomb. Remember to convert cm into meters. If not later wrong. Okay, so that is how you can find the area. Up there, you do the same thing. You can do count boxes first and then only multiply by the area of each box. Or you straight away calculate half times base, which is 2 cm, times, must remember convert cm later, times height. This goes up till 50, right? This is 50. This looks like 54. But we're going to estimate until 52. So let's do 52. So this will be from 28 up to 52. That's the height of this triangle. So 52 minus 28, whatever that length is. Okay, so let's try and see what we get for this method for area. Since we're looking at the graph, I'm going to use this area, add with this area, and we see what we get. So this one, must remember to convert the centi, underline the centi. Okay, what should we get? 0.24 for this first one. Volts. Okay, the area is volts. Sorry, not area is volt. Area is volts. Correct. Then the other one is 0.56. So right here, 0.56 volts, which is the area. Okay, which means in total, based on my rough estimation, the area under the graph here would be in total 0.24 plus 0.56, which is 0.8. So I understand there may be a whole range of answers, and the mark scheme does allow this too. So the mark scheme allows if your area is somewhere between 0.7 to 0.84 is okay. You may count boxes differently slightly, but as long as you get the area, you're okay. Alright, so that's the method of counting boxes. Let's go with 0.8 since I calculated that. Okay, back to this. So the first method here is to use area under the graph because potential energy, when you go from one position to another, is Q, the charge that is moving around, times the volts, which is the area under the graph. So area under the graph. So Q is 8.5 times 10 to the negative 9. Area under the graph was, what was our estimation? 0.84 up there. So we're going to write 0.8. Not 0.84. Oh, 0.84 is the official answer. Okay, 0.8. We'll stick with my answer. 0.8 times 8.5 times 10 negative 9. I should get 6.8 times 10 negative 9. So whatever answer you get, just write it in the answer line down below. For this method, the mark scheme has a pretty generous range of answers. So they accept if your potential energy is somewhere between 5.95 to 7.14 times 10 negative 9. So as long as you're in that range, super big range, you're okay. So they're very generous. Estimate lah, however you want to estimate. So this is the recommended method which I approve. 1 mark goes to the final answer. 1 mark goes to your area, whether you showed this working or you counted boxes. I just want to see whether that is between 0.7 and 0.84. Then it's okay. This is the C1. And firstly is the knowing that Q times area under the graph is potential energy. This is the first one. Okay? This is the area method, which I recommend. But you need to know, how does all these 4 pillars relate to each other? We just went from field to potential energy. We did the journey. There is another method by the mark scheme which takes the other route. From field, the graph, we find force. From force, then you find potential energy. But the way the mark scheme does it is a bit unsatisfactory. But I will show you anyway. This one is looking at method 2. Here, this is method 2. Method 1 recommended is down here in the mark scheme. Method 2 is the one on top. So what is it talking about? Okay. So when you want to find force from field, what do? F equals to QE, right? I'm going to call this the green path. Okay, so F equals to QE. But the question is, wait, which E though is changing? During this whole journey, you look at this part where I'm coloring green. The electric field strength is very different. So how the mark scheme proposes is to take the average. They say you increase from 28, right? I think it looks like 28. Yeah, it's 28. 28 increase up to 52. So 54, sorry. The actual intersection point is 54. So they say, find the average lah. Okay, so we find E average, which will give you the average force. Then from force, if you want to find energy, you can think back to your old, work equals to force times distance. But in this case, you can say potential energy equals to electric force times the distance traveled by the particle. So I'm going to write this down. EP or U equals to force, the average force, times the distance it traveled. That's how I can find that. So this is method number 2. Let's write it down. Number 2. First step. Force equals to QE. But we have a changing E, so we're going to use the average E and the average force. So this will be 8.5 times 10 negative 9 times the average. What was the lowest value? 28. Okay, we're going from this point to this point. 28 and 54. So average is just 28 plus 54 divided by 2 lah. Okay, we got our E. And this should give us a value of very small force. 3.485 times 10 negative 7. Okay, then next step. We go force times distance, because work done or energy is, change in energy is force times distance traveled. So we're going to take our 3.485. Of course, you can do all this in one step. Just writing it step by step so you can see. And we move 2 cm, right? So I can see. From 7 to 5, right? 7 to 5. Okay, 2 cm movement. So 2 times 10 negative 2. This should give us 6.97 times 10 negative 9. Joules of energy. Okay. It's kind of close, 6.8, 6.9. Again, there are many possible ways to find this answer. So the mark scheme, they round it off to 7.0, allow 1 SF. Okay, because it's an estimation. All right. They also mentioned that when you are reading from the graph 54, they allow plus minus 1 because it's a bit hard to see the graph and they acknowledge that, which is great. Now, the other method in the mark scheme, this one, I do not agree with what they are doing, so I do not recommend to do this. I don't even know why. Like, this is not correct. It's supposed to be dv e dx. It's not. Never mind. I will pretend I did not see that. Okay, so the third method is going back to our potential energy equation. This last method is not in the mass scheme, so I don't know whether it's accepted or not, but we'll show you anyway. So this last method, number 3. Man, we're running out of space. Let's go up there. Is there space here at all? Okay, let's do it here. So method number 3. Your favorite EP equals to KQQ over R. We all like to use these equations, but sometimes these equations are not suitable. But we'll try our best. We have a problem of we don't know the Q. So maybe we need to find what is Q first from this graph. So what I'm going to do first is, this is an electric field graph, right? So I need to find Q. I am going to say, all right, E equals to 1 over 4 pi epsilon naught KQ Q over R squared. And E, I'm just going to pick a random point, like maybe this point right on top, this tip. This is at 4 cm and 84 Newton Coulomb, this point. I'm going to use that and plug it into my equation. So I have 84 equals to Q that I want to find, 4 pi epsilon naught, and the R, which is 4 cm at that point, square. This should give me a Q of 1.495 times 10 negative 11 Coulomb. Ah, that is the Q of this big charge that created this graph in the first place. Okay, great. Now what? Now we can do our favorite equation. Okay, so now we find the change in electric potential energy, which has to be KQQ over R minus KQQ over R at the second position. So, oh man, this is a very long method, very mathematical intensive. Okay, let's go. So KQQ over R. Let's substitute the values in. You can factorize this out. QQ 1 over R1 minus 1 over R2. Okay, there's no space to write already, so I'm just gonna write it here. You substitute in your big Q and your small q for the charge. And remember your R, you start off at 7 cm and you go to 5 cm. Okay, with this method, you should get about 6.5 times 10 negative 9 joules. Okay, this is lots of methods. Do you have to know all? Well, it's good to know all. Of course, in order of preference, I recommend knowing number 1. Number 2 is acceptable, a bit sketchy, but I'm okay with it. Number 3 is okay, but there's a lot of math to do here if you use method number 3. Alright, so I think that's all for this question. 5 marks. Lots of methods. Make sure you know your 4 pillars. Gotta know the 4 pillars. If you don't know the 4 pillars and how they relate, important thing is the relationship between the pillars. It's gonna be a bit tough for the fields. So hope that was helpful in helping you find or understand these graphs a little bit better for electric fields. But that's all for this video. I'll see you in the next one.